Can you all hear me, right? Can everyone hear me? Hello, can you all hear me?
Yeah.
Okay, thank you so much. So I need everyone to put on this video. We're actually going to start at 10:10, the class time. I need everyone. So, like I said, I'm going to be taking attendance of those, uh, you know, take attendance, because, attendance is mandatory. So I want to welcome every one of us to this group presentation. Like I said, I want everyone to put on his video. Okay, I want to see everyone behind the scene. I want to see everyone behind the camera. Okay, so the presentation today, we're actually gonna have group one. So I think group 1 to 5, and each group actually gonna spend 5 minutes. And after 5 minutes, there's going to be question and answer. Okay, after 5 minutes of presentation. So I need every student to put on their video because you have to put on your videos. Everyone, put on your video. I'm seeing some student right now, they are not putting on their video. So you have to put on your video. I'm actually going to be I'm taking attendance right now. Okay, of those who actually put on their video. It's compulsory. Okay, taking attendance right now. We are starting at 10:10. Okay, the first presenter should be ready at 10:10 a.m. I'm actually gonna call. Like I said, I'm taking attendance right now. Maybe.
Okay, now it works.
Okay.
Let me
Now
know when
your
you're ready.
now your time starts now.
Okay, hi, we're group one. So our topic was Gaussian mixture modeling and specifically with the Palmer Penguin dataset. So I'm going to go over an overview of what we're going to talk about today. So general overview of GMM and its relevance, and then how we implemented it with the data set, and then results from clustering, and then comparative analysis with that, and then any concluding remarks, including limitations we found, and then followed by a Q&A session. So to start, I'm just going to go into the understanding the fundamentals of GMM. So brief overview, GMM represents data as a mixture of Gaussian distributions, making it ideal for capturing complex patterns, and then some key characteristics of GMM. So each Gaussian distribution has its own mean and variance, allowing the model to adapt to clusters of different shapes and density, sorry. And then for applications in clustering analysis, so GMM is widely used for clustering as it can adapt to data structure and provide soft assignments of data points to clusters. And then here I'm going to go into the steps of the EM algorithm. So a brief overview is EM algorithm refines those GMM parameters and then iterates between the E and the M step. And then for initialization, you start with the initial guesses for the means, covariances, and the mixing coefficients. And then for the expectation steps, you calculate the responsibilities, which is the probabilities of the data points belonging to each cluster, and then use Gaussian probability density functions and current parameter estimates. So as you can see, the formulas down below. And then to the right, we see the maximization step or the M step, which we update the parameters to maximize data likelihood, and that updates the means, which is including in the formula below, variances, and then the mixing coefficients, as I mentioned before. And then now I'm going to go over the data set. So we use the Palmer Penguins data set. So for species classification, our data set included 3 penguin species, Adelheid, Chinstrap, and Gentoo. And then some key features about our data set is the bill length, depth, flipper length, and body mass that we kind of looked into. And then the objective for using this data set is to apply GMM to identify 3 distinct clusters. And then we want to test GMM's ability to represent and separate biological variation. And then here's the methodology. So first we used a BIC plot to determine the optimal node clusters. Then we employed the M cluster function parameter estimation and data assignment. And then we used the FBIS cluster for visualization, so for plotting the points. And then we created a comparison table to evaluate cluster alignment with the actual species itself. And then here we're going to look into the results of GMM clustering. So it was found from the BIC plot and above that 3 clusters were optimal. And then for the Adelite species in red and chinstrap in green, they're found to overlap, but then you can see that Gentoo in blue does not overlap with those. So from this, we can see GMM effectively identified species clusters, although there is some overlap between Adelite and chinstrap. And then for the comparative analysis, we use k-means, k-medioids, and dbScan. So for k-means and k-medioids, we saw that they both struggled with overlapping species and they didn't perform well in separating the penguin species, and dbScan failed to identify any meaningful clusters, as you can see on the right. And then here's a comparison table, kind of visualize this a little bit better. So the key point of this table is we want to just see the performance of the different algorithms in clustering penguins by CDCs and then the expected amount on the end. So GMM, obviously we mentioned before, it accurately clustered Adelite, chinstrap, and Gentoo into separate groups, but k-means and k-medioids struggled with that overlap and incorrectly grouped those penguin species, and then dbScan failed ultimately to produce any clusters. And then for model evaluation, so again, a no, GMM performed the best for the penguin dataset out of all the other models we tried, and some certain limitations to note though. So we use hierarchical clustering for initialization, so it might not always be optimal. And then we relied on BIC to select the number of clusters, but we could have used other methods to explore, such as like AIC. And then we did exclude rows with missing data values, so this might have led to the loss of potentially valuable information in our data set. And then kind of just to conclude, so the key point again, GMM performed exceptionally well in clustering penguins by species. It outperformed k-means, k-medioids, and dbScan in handling those overlapping clusters. But one thing to add, however, in cases with no overlap, it might be harder to gain clear insights into the complexity of the data, understanding the data structure, basically. Now I'm going to open the floor to any questions or discussion.
Okay, so can we give her a round of applause? Thank you so much. When we want to clap, we can unmute to clap. And after, before I'm actually going to comment on that, I think I've already written down the names of those who put on their videos. It is compulsory when you join the Zoom for presentation, you have to put on your videos. I did not write down the name of the student that did not put on their videos. I just wanted to take note of that. If you don't put on your videos, you have to do that immediately because we have to see you. It's part of the grading system. We have to see those who are behind the scene. Okay? I've seen a lot of people. I think about seven, 1, 2, 3, 4, 5, 6. Let me see, seven students that did not put on their video. So I'm not going to write their name down. Okay, so now let me say you have an excellent presentation. As far as I'm concerned, you actually spend exactly 5 minutes. That is commendable. Okay. Before I'm going to make suggestion, I actually want members of the floor to ask question if there's anyone, any question. Okay. So you can go ahead if you want to ask question from the presenter. Is there anyone want to ask question? If you want to ask question, you can just go ahead. Okay, so I have 5 students that are not open their camera, so I'm not going to write their name. Because that is compulsory. I have to see people behind the scene. So you have to put on your camera. Okay, so let me say to the presenter, my only question is I wanted to go to the table of comparison. Can you go to the table of comparison
Yeah.
where you know where you are comparing the algorithm, different kind of algorithm. Okay, yeah. So why is it that the density base or the DBSCAN, okay, is there any reason why that was not able to have any clustering, you know? So what is the reason behind the NA in the DBSEAN? What do you
Okay.
think could cause that?
I know, Hajar, I don't know if you want to chime in because you did the
Yeah.
R for this and kind of explain what happened, but
Yeah, so hi everyone, I'm Hajar. I'm the person that did all the data analysis stuff. So yeah, I've when I was doing DB scan, I was experimenting with different min points and epsilon values, and for some reason, upon doing it in R, it wasn't able to identify any clusters or anything like that. So one potential reason could be um, a mistake in doing the R code. That could potentially be. Second, it could just be that this data set is just not really made to be used with DBScan.
I can also
Okay,
add,
is there any other reason?
I'm in the same group. I think it also might have been that because CB scan like clusters points that are very closely packed, it could be possible that none of the points were close enough packed for it to separate them based on like the density and like the different values we chose.
Okay, so you said it could be possible that none of the points have high density, right? Is that what you mean? Can you say that again? You said it could be possible that none of the point what?
I think it could have been that like because DB scan does it based on like closely packed points, like where there's extremely high density, it might have just been due to the values we chose. They weren't like packed enough for it to decide that they're clusters.
Okay, so they are not packed enough to
Yeah.
be classified as clusters.
Yeah.
Okay, so I want to for say this you know for sincerity, I can see, you guys you've done a great job and you are sincere with this because I know some some people like, okay, let's just put something there, even though we observe that. So my only recommendation, you're still going to submit your final draft, right? My only recommendation here is take a look at the arrow codes again. Somebody talk about, oh, maybe I have to look at the arrow code. Check the arrow code and make sure, and also check that maybe it may be due to the fact that they are not packed enough, and because of that, DBSEA. So I just wanted to investigate that. So that's going to be in your report, the reason why there is any. Aside that, I'm actually going to say, you guys have done a very great job with excellent presentation, and I like the way you responded to questioning. So let us again give them a round of applause. Group one, let's give them a round of applause. They've done a great job. Yeah. hmm Okay, now you can stop your share. So you're going to wait from me because after the whole presentation, you're going to receive post presentation comments from me, for a particular group, what you need to improve upon. You are likely going to get that before the end of today for those groups that are going to be presenting. Okay, so is group two ready? Group two ready?
Yes.
Yeah, share your screen.
Can you see it?
Yeah, we can see.
Okay, awesome. All right, yeah, so our group was clustering-based algorithms. We ended up choosing K-means as our clustering algorithm and utilized a credit card usage data set to find some customer behavior patterns. So here's an in-depth summary of the K-means algorithm. It was first proposed and published by James McQueen. Basically, it creates groups of data points based on the relative distance to the mean or center of a cluster. and calculates the sum of squared errors using Euclidean distance, identifies the centroid of each cluster, and then assigns data points to clusters based on that distance. You can see in the right is some pseudocode of how you can implement it. Some advantages of k-means is you can easily detect outliers, and there are many good methods to find optimal number of clusters, such as the elbow method and the silhouette method, which we've talked about. Here's a little more background on how we use the algorithm. In k-means, there's a predefined number of clusters, unlike something like dbScan. And each observation is assigned to exactly one cluster. We computed the centroid to reassign observations to a more suited cluster based on that Euclidean distance. And we use the elbow method and silhouette method to determine our k-value, or number of clusters. See, the right is the mathematical equation of how k-means works. So as I said before, we used credit card customer data from Kaggle. There's a big range of features such as spending habits, age, marital status. And yeah, using this data, we wanted to help identify stable and valuable customers. So the results of our elbow method and silhouette method is we found clusters 2 and 7 to show promise in finding good patterns. And we'll go next. We'll show you the elbow method. Here's what we found. This one is a bit harder to find the optimal number of clusters, but we saw a bigger reduction in 7 and 8, kind of more than anything else. So we decided to go with 7 clusters for the elbow method to try out. And then the silhouette method, you can see an obvious separation at k equals 2. So from both of these, we're going to try out 2 clusters and 7 clusters. Here is our 2 cluster solution. You can see clear separation in this 2D space, with the blue being high engagement and the red being low engagement. So we kind of assigned those words to each cluster based on their mean values of each cluster based on some features. But yeah, and we also use the fviz package in R, which uses PCA to reduce the dimensions so we can get a clear look at what our clusters look like. But yeah, so here's our 2 cluster solution, and then here's our 7 cluster solution, which is a little more niche, but you can see the low risk, higher values, and like a premium segment. So overall, 2 cluster solution provides optimality for strategic decisions, so like longer term goals, and our 7 cluster solution is valuable for tactical planning, or maybe some like short-term advertisements. And yeah.
Okay, can we give this presenter a round of applause? Thank you so much for wonderful presentation. So this is another excellent presentation. Of course, you are making my day today. So I'm really so happy. Okay, before I'm gonna make my comment, is there any question?
I have a question.
Okay, go ahead.
How did your group figure out, like, so you had for k equals 2, that's like low engagement and high engagement, and then you had for the k equals 7, you had like all these different like categories. Did you guys figure it out by analyzing the data afterwards and being like, okay, this is kind of what it would fit, or was there like some sort of method you used in order to try to figure that out, or was it just like analysis, I guess?
Yeah, it was kind of like real world on that, like just using prior knowledge and looking at the means of each column in each cluster is kind of what we looked at to find those.
Okay, that's awesome.
Thank you. Any other question? I just need a practical meaning because I know you work on the credit card. So what do you mean by when if I happens to be a customer, right, that is classified as high engagement, what does that mean in a practical term? Like for to somebody that is not in statistics and data science, what does that mean?
Yeah, I should have
Got this
mentioned
one.
yeah, go ahead.
So the high engagement customers, typically that's the credit card that is called first in wallet. So the one that you go to the grocery store and the first one you pick out of your wallet, your general purchase card that you use for most day-to-day things. Low engagement would be perhaps you only use this credit card at certain places because it offers better rewards, or perhaps you don't use the credit card very much at all.
Thank you so much. That's a wonderful response. Okay, for like I said, I think you're gonna be waiting for my post aside, post presentation comments today. So on how, but I'm actually gonna say at this time, this is a wonderful presentation. I've gotten a wonderful response from the group members. Can we appreciate them one more time? Thank you so much. Okay, group three ready?
Yep.
Okay, got the floor.
Good. All right. So we're doing probabilistic graphical models. PGMs visually represent the variables and dependencies, and we're doing a study that utilizes Bayesian networks to model a medical diagnosis scenario involving 2 diseases which are marginally independent and 3 symptoms that are conditionally dependent on their respective diseases. And it has 8 independent parameters. So Bayesian networks are a type of probabilistic graphical model that represent a set of variables and their conditional dependence using a directed acyclic graph. And the nodes represent the random variables and lines show dependencies. And they're widely used for diagnostics, decision-making, machine learning, and their ability to model complex systems and visually simplify data. Although there's other types of PGMs, we're focusing on Bayesian networks because we spent the most time doing that in class. And there's also undirected graphical models with like Markov random fields. And those are where the nodes have mutual dependencies. So our implementation is a patient goes to the doctor for a medical condition, and the doctor suspects 2 diseases as the cause of the condition. The 2 diseases are D1 and D2, which are marginally independent from each other. And there's 3 symptoms, S1, S2, and S3. S1 only depends on D1. S2 also depends only on D1, and S3 depends on D2. All the variables are Boolean, so they're either true or false. And this is the R implementation. If you're using the code and doing Bayesian networks, make sure you do tidyverse, lubridate, and bnlearn for your libraries. And then we implement the data, and then it shows this. And this is the Bayesian network. So we want to write the expression for the joint probability distribution as a product of conditional probabilities. Basically, since D1 and D2 are independent, you just do PD1, PD2. S1 and S2 are dependent on D1, so the probabilities are S1 given D1 and S2 given D1. S3 is dependent on D2, so it's S3 given D2. And then multiplying all these is how you get the conditional probability, product of conditional probabilities. So let's say there's a probability of having disease 2 is 0.01, and the probability of having symptom 3 is not having it is 0.99. If someone has disease 2, there's a 0.8 probability they will have symptom 3. If someone does not have disease 2, there's a 0.1 probability of them having symptom 3. How can we find the 2 missing pieces of this data? Well, all we have to do to find the missing pieces of data is to find their complements, since they must add to 1. So we just take 1 minus 0.8, and the probability that having D2 while not having S3 is 0.2. The same can be done to find probability of not having D2 while also not having S3. So we just do 1 minus 0.1, and then we get 0.9. So this is our final probabilities for the Bayesian network distribution. If we want to find the number of independent parameters, we know that D1 and D2 don't depend on any variables, so they just have one parameter each. And then S1, S2, and S3 all each depend on only one parameter, so they're all 2. So 2 plus 2 plus 2 plus 1 plus 1, total of 8 parameters. So main insights, disease 1 and 2 depend on each other. Symptoms 1, 2, and 3 each depend on only one disease. The total number of independent parameters required to describe the joint probability distribution is 8. Potential improvements was including more diseases and symptoms to broaden diagnostic capability. But since we're only allowed 5 minutes, it would take too much time including all that. And then usefulness for Bayesian networks is just to simply show the things and visually show how they coordinate with each other and the probabilities that depend on each other. Any questions?
Okay, so can we give him an can we appreciate him? Okay, thank you so much for the wonderful presentation. So let me first let's get a question from the floor before actually give my suggestion. Is there any question? Okay, so you actually work on probabilistic graphical model, and I can say that you actually talk about, you figure out the number of independent parameters required for conditional distributions. What I'm going to advise that you also do is, okay, situation where you are to, without Bayesian network, what would have been the number of parameters? Because you need to be able to show the world the numbers of parameter that you are able to save in a parameter space, because you ended up with 8. Okay, if I want to figure out the probability of the joint and without the Bayesian network, okay, you need to be able to tell us how many parameters are we likely going to have if we want to achieve the same goal. Okay, make sure you include that in your report. Okay, and not only that, what is going to be the benefit of using the Bayesian network, and what is going to be gainful? What is the meaning? If we want to find the probability of the joint, you're talking about disease and symptoms. Okay, somebody that is not in statistics or in data science, we really want to understand the message you are passing across. What is the meaning of the probability of the joint? Joint of what? Occurrence of what? You also need to incorporate that in your report. Does that make sense?
Yep.
Okay, so once again, thank you for the presentation. Can we give them a round of applause again? Okay, so I want to go into group 4. Is group 4 ready?
Yes.
Okay, share your screen. You got it, floor. You got 5 minutes.
Good morning, everyone. Today I will present on clustering-based algorithms and essential technique in unsupervised machine learning. My name is Yiming Xu on behalf of Group 4. Our focus will be on 3 commonly used clustering methods: k-means, k-medoids, and hierarchical clustering. We will explore their theoretical foundations, practical applications, and key differences. To illustrate their performance, we will use the Pima Indians DIBIS dataset, a real-world example that demonstrates the strengths and limitations of each method. So let we first look at the background of the clustering-based algorithms. Clustering is a method of grouping data points based on their similarity and with the objective of maximizing similarities within clusters and minimizing similarities between clusters. Unlike supervised learning, clustering works without labels, making it invaluable for discovering hidden patterns. It's widely used in fields like customer segmentation, anomaly detection, and biology, where finding natural groupings is critical. For example, in healthcare, clustering can help identify patient subgroups based on symptoms or clinical features. And to better understand clustering, let's cover some foundational ideas. For the similarity measures, algorithms often use matrices like Euclidean distance or Manhattan distance or cosine similarity to evaluate the closeness of data points. Each matrix captured a different aspect of the data's structure. For optimization, the goal is to minimize intra-cluster distance and maximizing inter-cluster distance. For clustering structures, clusters can be hierarchical or create nested groups suitable for multi-level analysis or partitional, which creates distinct and non-overlapping clusters, ideal for straightforward applications. And now is our k-means example. In the Premier Indian database dataset, we applied k-means starting with k equal to 2 clusters. The process included standardizing the dataset to ensure all features contribute equally and randomly initializing scene choice and iteratively assigning points to the nearest clusters and recalculating scene choice. So this is our visualization of the k-means cluster. And I want to show this one. Yeah. So we realized the two distinct groups, but some overlap suggested the need for some clusters. Using the ALBA method, which plot within cluster sum of squares against k, we found that k equal to 3 was optimal. This balancing point captured meaningful groupings without overfitting to noise. And this is the visualization. We can see it is spherical. For the chemidoid example, chemidoid clustering improved robustness by using middoids instead of centroids, making it less sensitive to outliers. We segmented the same database to 3 groups. The visualization showed distinct clusters, but minor overlaps remained. To evaluate clustering quality, we used Selossi scores, which measured how similar points are within their cluster compared to others. Cluster 2 has the highest Sihordi score, indicating strong cohesion and separation. However, some points in cluster 1 showed negative scores, suggesting misclassification or weak boundaries. And now we talk about hierarchical clustering. Hierarchical clustering offers a different perspective of building by a dendrogram, which reveals relationship across varying levels of granularity.
You have 1 more minute.
Yeah, sure. Using Wall's method, which minimize variance within merged clusters. At k equal to 3, the clusters was distinct but slightly overlap, and increasing k equal to 5 or 6 further reduced the overlap but fragmented clustering. And the flexibility allow us to explore the dataset structure without predefining k. And now we draw into the conclusion. In conclusion, k-means is effective and widely used. This algorithm calculates cluster centers at the mean of the assigned points. However, it assumes spherical clusters and it is sensitive to outliers, which can distort the results. And for chemidoids, a more robust method that uses extra data points called middoys as cluster centers. This reduces the influence of the outliers, but requires more computational resources, especially for large data sets. And for hierarchical clustering, the method builds a dendrogram or a tree-like structure, showing how clusters are formed at different levels. It doesn't require predefining the numbers of clusters, making it flexible but computational slower. And each method has its own strengths and own shortness. So through this analysis, we gain a deeper understanding of how clusters can uncover hidden structures in the data. Thank you for your attention. And any questions are welcome.
Okay, so can we give her a round of applause? Okay, so is there any question from the audience? Is there any question from the audience? I actually wanted to go back to the clusters. Can you share your screen? I want to take you back to clusters.
Sure.
Okay, so where you got the 3 clusters, where you got 3 clusters.
Here.
Yeah, yeah, 7, slide 7. Okay, here. Okay, so I only want to make a suggestion. I actually believe that your intention was to compare the K-mean, the K-middoid, and the hierarchical. So, but I'm actually seeing a picture. The picture that I'm seeing right now is I'm seeing an overlapping picture. And you know what we mean by overlapping? There's another clustering algorithm that is very, very good. So for situation where objects can be in more than one group, as you can see, what this particular K-middoid is actually showcasing. So what I'm going to suggest is can you also compare GMM, can you compare the Gaussian Mitchell model of clustering with the 3? Can you hear me?
Yeah, I can.
Okay, so I'm actually making that suggestion because of what I'm seeing right now, because I'm seeing the clustering, the clusters overlap.
Yeah.
Do you also see it yourself?
Sure.
Okay, and the K-middoid, the K-means, and the like, they are partitioning, you know what I mean? Partitioning clustering, right? Okay, so but from what I'm seeing right now, so that's why I'm making that suggestion to also consider comparing the Gaussian mixture base of clustering that also handle overlapping with the K-mean, K-middoid, and hierarchical, and that would be super excellent. Does that make sense? Did you get that right? Did you get that? The
Yeah.
presenter? Okay, so once again, thank you for the wonderful presentation. Can we give her a round of applause once again? Okay, so we're gonna group 5, which is gonna be the last group of the day, but not the least. Is group 5 ready?
Yes.
Okay, ready to listen to you. You got the floor.
Could you guys see my screen?
Yeah, we can see your screen.
Okay. Okay, I will be.
Can you make it bigger?
Yes, for sure.
Yeah. Okay, that's better.
Okay, I will start now. Hi, everyone. We are group 5. Our topic is hierarchical algorithm link method. So from the lecture, we know hierarchical algorithm is one of the clustering approach, and we list 4 different linkage. Single linkage is the shortest distance between clusters. Complete linkage is the longest distance between clusters, and the average linkage is average distance between all points. And the worst linkage is minimize the variance increase. That's for different language. And today I will talk about the intro to datasets, compare and analyze to our situations and our conclusions. So first, why we choose hierarchical algorithms? Because it's interpretability in cluster text, and we're interested in 4 different types of method, and we want to get to know the 4 different languages in detail and find the best one in our context. Intro to our dataset, we choose Percept in our website, which is annual perception in US cities. To the background, we are the 4 agricultural developers. We hope to choose a suitable city in United States for our agricultural project. We will focus on analyzing annual precipitation data for United States cities to help plan the farm locations. And then these are the code from a lecture we applied to get our dendrograms. These are the dendrogram we get from the previous R code, and right now we want to find the best language for our situation. So we use the AC code, which from the lecture, the closer the value is to 1, the clearer and the more reliable the clustering structure is. So from this 4 value, we can find what language has the most close to 1 value. So we choose, in this situation, we will choose the words language. After choose the words language and we want to classify the level of the cluster in our situation, we use 3 methods. And for the elbow method and the gap statistic, we can get the most reasonable K value is 4. So depends on the words language, we will have 4 levels of clusters. And then we also did a scatter plot. From here, we can find the clustering is relatively reasonable because there is no significant overlap between 4 clusters. And then we also did a geographical distribution map. And this is a reasonable map because we can find that the coastal areas might have the higher precipitations due to their close to the ocean areas. And inland and regions could belong to the cluster with lower precipitations. With this clustering plot, the question we can be answered are which cities have similar precipitation patterns? What are the characters of precipitations in different regions? And we also did a bubble map combined with precipitation size, so we can get more informations from here. And then we also did a box plot to analyze the cluster center. For the cluster 1, which is the red box here, it's wet area with high annual precipitations, including cities like New Orleans. And cluster 2, which is the green box here, is dry areas with low precipitations, including cities like Phoenix. And then the cluster 3 is moderately dry wet areas, including cities like Atlanta. And cluster 4 is a purple box here, is moderately dry areas, including cities like Chicago. Back to original question, based on the analyze, we may choose a city in cluster 3 and cluster 2, which are moderately rainfall and dryness. These are the region around like Midwest region and Great Plains. In addition, we need to assess outliers and identify outliers within each cluster. As a city with significantly lower or higher precipitation compared to other cities may need additional consideration for irrigation or flood protection. Conclusion: in this project, we analyzed the annual precipitation in U.S. cities using a hierarchical algorithm to support region agricultural development. After determining what language are the best method, we utilized the scatter plot, link plots, geographical distribution, and bubble plots to identify 4 perception zones: dry, moderately wet, and wet. The zones will guide irrigation and crop planning. While effective, this method has limitations, including data may outdate it because we choose from the ARC website, and the exclusion for other environmental factors. Thank you for listening. The additional R code will provide in the group project draft. And any questions?
Can we give her a round of applause, please? Thank you so much for the wonderful presentation. I think I welcome. Is there any question from the floor? Is there any question for the presenter? Okay, so let me say the this topic is well presented and of course very, very clear. You're trying to compare linkage within hierarchical clustering based algorithm. And of course, you're able to identify the word linkage, and that was what you eventually use. I'm going to say this is highly commendable because there is no question. I don't have any suggestion as far as this is concerned than to say, Group 5, you've done a very beautiful work. Now, let me also say this today, Group 1, Group 2, Group 3, Group 4, Group 5, you all exceeded my expectations and you deserve some accolades. So I want to thank every presenter today and everybody that work behind the scene to make sure, you know, you have your beautiful presentations. So even though I'm still going to make some suggestion later before the end of the day, to better improve the quality of your work. So you're actually going to receive something from me today. So also going to include the dates that your final submission is expected. So once again, all the groups that made presentation today, I'm actually gonna say based on what you presented, is they are excellent. You all have excellent presentation, and I hope the presentation on Wednesday will be more than excellent. I'm also hoping for that. So you have done a very great job. I've already graded exam 2. And of course, there are some students that, their submission are not